Good morning all. This is Dr. D. Khalandar working as Associate Professor in the Department of Electronics and Communication Engineering, Institute of Aeronautical, Dundigal, Hyderabad. Today I am going to discuss a few programs related to 8086 like a message displaying on CRT, binary to a gray code conversion, and BCD to binary code conversion under the course Microprocessors and Microcontrollers. So the slides are prepared by referring the textbook Advanced Microprocessors and Peripherals by IARE and Budchandi, publication Tata McGraw-Hill Publications. So the first program is write an ALP for displaying the message. The study of microprocessors is interesting on the CRT screen of the microcomputer. For writing this program, first we will initialize the data segment and the assembler will assign the addresses for code segment and data segment. For that we use assume directive. So we require two segments, one is for code segment and one is for data segment. So we write CS:code, DS:data, where this code will contain the address of the code segment, the data will contain the address of the data segment. Now we will declare the data segment. Under this data segment, whatever the message which we are having, that we are going to be placed in the data segment. So the start of the segment will be start with the assembler directive segment, preceded with what kind of segment we are going to start. So write data segment indicates the data segment starting. In this data segment, from the segment to endes, so whatever the entities are there, that will be corresponding to that particular corresponding segment. So endes is the end of the segment directive. As it is for data segment, we will precede that one with data. So within this data segment, we are going to have a message, where this message, each and every character is going to have dB, which is a defined byte. Next, this 0DH and 0H are the limiters for indicating the start of the string. So what are the string which you are going to be display, that we have to enclose in double quotes. So we are going to display the study of microprocessors is interesting. Then the delimiters 0DH and 0H followed by dollar symbol. This is the format for writing a message in the data segment. So before seeing the program, first we will say the instructions, what are the significance of each instructions. So as we are using the data segment, the address assigned by the assembler, we have to load into the data segment register. So we can't load the address of the data segment directly into DS register. We have to move that one in indirect manner. So first address will be moved into AX register, from the AX register to segment registers. So these set of two instructions are used for loading the data segment address into the DS register. Next, move AH, 09H. The purpose of this 09H is, so for displaying the messages on the CRT, we had to enable the function with the corresponding value as 09H. This we had to load into AH register. So load AH register with the 09H to set function value for displaying the message. Next, whatever the address of the message in the data segment, that will be fetched by the directive offset. So offset directive will fetches the offset value of the data set, whatever the variable which you are placing in the data segment. That will be loaded into a DX register. So for that, move a DX, offset of message. Then we will raise the interrupter 21H for displaying the message onto the CRT with the function value 09H. Next, once the message is displayed on the CRT, then we have to terminate the program. So for that, we use move AH, 4CH and INT 21H. Now the program at a glance. Code segment indicate the start of the code segment. Start indicates the label for start of the program. So the first two instructions for loading the data segment address assigned by the assembler into data segment registers by using the instructions move AX, data followed by move DS, AX. So first the address will be loaded into AX register, then AX register contents will be loaded into data segment register. Next, for setting the function for display, we will load the function value, that is 09H, into AH register. So for every INT21H instruction, whatever the function which you are going to execute, that we have to load into AX register. For each and every function, there will be a corresponding value. So for displaying the message on the CRT, we have to load the code value as 09H into AH register, then INT21H. Before that, we have to load the offset address of the message in the data segment into DX register, then issue the INT21H. So these three instructions for displaying the message. Next, once the data is displayed in the CRT, we have to terminate the program by calling the interrupt INT21H. For returning to the DOS prompt, we will write the function code as 4CH. So move AH, 4CH, INT21H. So these two instructions for terminating the program and returning to the DOS. So for end of the segment, we use end-s. As we are ending the code segment, we will precede this one with code. To end the program, entire program, so we use end directive. The program starting a label as start. So this is the program for displaying the message. Next, write a program to convert a 8-bit binary number into equivalent gray code. So let us assume for converting this conversion, how it will be takes place. First, let us assume the binary format, we are having the binary bits from B0 to B7. Then the coded gray code will have the bits from G0 to G7. So this is a 8-bit gray code, whereas the input is, so this is input, which is a binary number, and the gray code, which is a output. So how we can convert the binary number into a gray code is, as we know, gray code is a unit distance code. For every two consecutive binary codes, we may have more than 1 bit change, whereas in the gray code, two consecutive numbers will be differ by only 1 bit. So for generating the gray value or gray code for the binary number, so if you have B7, B6, B5, B4, B3, B2, B1, B0, for generating the gray code, we will pass the first MSB bit as it is, that is B7. The next bit will be generated by doing the XORing between B7 and B6. That will generate this. I'll take as gray code 7, which is nothing but binary 7. Next, you will get the gray code 6th bit, where gray code 6th bit is B7 XORing with B6. Next, B6 will be XORed with B5 but generating G5. B5 bit will be XORed with B4 bit for generating gray code 4th bit. B4 XOR with B3 for generating gray code 3rd bit. Next, B3 will be XORed with B2 for generating G2 bit. B2 will be XORed with B1 for generating G1 bit of gray code. B1 will be XORed with B0 for generating the LSB bit of the gray code. So here we will write the expression as G7 is equivalent to B7, whereas the next numbers are the next digits of gray code will be generated as GI is equivalent to, where we are going to XR the, if we have sixth position, we are going to XR with the sixth and seventh position. So that will write B of I XORed with B of I plus 1, where I will take the values from 0 to 6. So this is the logic for converting a binary number into a gray code. Now we will see the programming part. So in the programming part, so what we will do is, we will take the binary number B7, B6, B5, B4, B3, B2, B1, B0. Then we will rotate these contents towards the right side by 1 bit. So here we are going to get B7, B6, B5, B4, B3, B2, B1. This B0 bit will be placed into carry flag. And here, before executing this instruction, we are going to clear the carry. So this 0 will be placed. Then we will apply the XOR between these two data, which will give B7 XOR with 0 is B7, which is nothing but G7. B6 XOR with B7 will generate a G6 bit of gray code. B5 XOR with B6 will generate G5 bit of gray code. B4 XOR with B5 will generate G4 bit of the gray code. B3 XOR with B4 will generate the gray code bit of 3, G3. Next, B2 will be XORed with B3 for generating G2 bit of the gray code. B1 XORed with B2 for generating G1 bit of gray code. Next, B0 bit will be XORed with B1 bit for generating 0. So this is the logic which we are going to use for writing a program. So first, we will initialize the data segment with input, which is a binary number, and we will reserve the memory for output, which is a gray code. So for assigning or requesting the assembler for assigning the memory for code segment and data segment, we use assume directive. Assume CS colon code, DS colon data. So assembler will assign one segment address for code segment, one segment address for data segment. Next, we will write the data segment with the directive segment, the start of the segment, and end as directive for indicating the end of the segment. As this one is corresponding to data, so we will proceed this one with the data. Next, in this data segment, we are going to have two variables. One is binary variable, the second one is gray code. So for binary, we are going to equate with some value, that is 34H. Next, gray code, which is a result. So for that, just we will reserve the memory without any initialization. So what could be the output we can expect is 34H is the input. So 34H we will write in the equivalent code as 0011, that is for 3. For 4 is 0100. So for converting, this is the binary input. The gray code will be generated as, the first bit will be kept as it is, that is 0. The subsequent values will be generated by XORing the current position with the previous positions. So 0 XORed with 0 will get a 0. 0 XORing with 1 will get 1. 1 XORing with 1 will get 0. Next, 1 XORing with 0 will get 1. Next, 0 XORing with 1, we are going to get the value as 1. 1 XORed with 0 will generate the output as 1. Next, 0 XORed with 0 is 0. So after converting the binary number into its gray code equivalent, the value which we are going to get as 00101110, which is the gray code. So the gray code value is 0010 is 2. 1110, which is equivalent to E. So the gray code equivalent for the given input 34H is equivalent to 2EH. That we can say after executing the program in this memory location. Now we will see the sequence of the instructions which has to be executed for generating the gray code. So first we have to load the data segment register with the segment address assigned by the assembler. So which is there in the data variable that will be loaded into AX from AX to DX. As data loading into data segment directly is not permissible. Next, the input number, which is a binary, that we are going to be loaded into AL register by using the instruction move AL comma binary. So this instruction will load the AL register with the input binary value. So as we want to XOR by shifting the contents towards right side by 1 bit, so we will take one more copy into BL register by using the instruction move BL comma AL. So now AL will have the number, binary number, as well as BL is also will have the binary number. So as we want to clear the carry flag, so for that we use CLC instruction, which is for clearing the carry flag. So here we have a BL register contents as well as AL register contents with the same contents, that is from B0 to B7 bits. Next, we will shift this contents of AL towards right side by 1 bit for generating the gray code along with the carry flag. So for that we use the instruction RCR. The register whichever we are moving is, that is rotating, is AL register. Along with the carry flag, how many times is? Only one time. So for that we write RCR AL comma 1. So now the AL register contents will be shifted towards right side by 1 bit along with the carry flag. So BL will contain B7, B6 until B0. As we are shifting the contents of the AL register along with the carry flag, and initially carry flag is initialized to 0. So we are going to get here it is 0, then B7 until B1. So this is AL register contents. So the next step is we want to XOR these two contents. So next instruction, right? XOR BL comma AL. So this instruction will XOR the contents of BL register with AL register. Then the output will have in BL register, so which is contained the BL XORed with AL contents. So the result now it is there in BL register. So now we will fetch the address of the gray code which is assigned in the data segment by using the instruction move DA comma offset of gray. So where gray is the variable name which we are assigned for gray code in the data segment. So that address will be fetched into DA register. Now into this memory location, we want to move the result which is present in BL register. So for that we will write the instruction move in square braces DA comma BL. So this instruction it is for moving the result which is there in BL register into the memory location. So what is this DA will contains? DL will contains the address of the gray code value, a gray variable. So into that memory location we are going to load the BL register. So as we have done the gray code conversion and the result is, which is a gray code, will move into data segment register. Now we can terminate the program, and to return the DROS prompt, we execute int21h. Before that, the function code, that is 4ch, will be loaded into AH register by using the instruction move AH comma 4ch followed by int21h. So by executing these two instructions, the program will be terminated and it will return to the DOS prompt. Now we will see the program at a glance. Code segment indicating the start of the segment, which is belongs to code segment. Next, a label is given for the start of the program, the start label. The first two instructions for loading the data segment address assigned by the assembler into DS register indirectly first moving the address into AX register, from AX register to data segment register. The next instruction is loading the input, which is a binary number, into AL register by using the instruction move AL comma binary. As we want to shift these contents and XR with the same contents, so we are going to have same binary number will be loaded into one more register, that is BL register, by using the instruction move BL comma AL. Next, in the MSB position, when you are rotating these contents towards right side, we want to have the MSB position is equivalent to 0, which is the carry flag. So we will clear the carry flag by using the instruction CLC. Then we are going to rotate the AL contents towards the right side along with the carry flag by one time. So for that we use the instruction RCR AL comma 1. Next, we are going to XR the AL register contents with BL register contents. So this instruction will do the XR operation with the AL contents with the BL, and the result, which is a gray code, which will be exist in BL register. Now this result we want to move into the data segment where we are reserved a memory for gray code. So first we will fetch the address of offset of gray code number by using the instruction move DA comma offset of gray. This will fetches the offset value of the variable gray into the DA register. Now the result which is present in BL register, we are going to be load into that memory location by using the instruction move in square braces a DA, which is pointed to the memory location. Into this memory location, we want to load the BL register contents. Next, we want to terminate the program. So for terminating the program and for returning to the DOS prompt, so we are going to execute int21h by calling the function which is having the equivalent values 4ch. So for that we use the instruction move ah, 4ch, then we will generate int21h. So to end the code segment, we will use code endes. So endes is the directive, assembly directive, which will indicate the end of the segment. Next, to end the program, we use the directive which is end. End is the directive for indicating the end of the program. Then the program wherever it is started, that label we are going to be provided as postfix for end. So this is the program for converting the binary number into gray code. The next one we will see write a program to convert the BCD number into equivalent binary number. As we know, BCD stands for binary coded decimal. This binary coded decimal number we have to convert into its equivalent binary number. So the sequence of the instructions which we are going to use, we will see. First one is, as we are using the data segment address assigned by the assembler into the data will be loaded into data segment register indirectly by moving into AX register from AX register to DS by using the couple of instructions like move AX comma data followed by move DS comma AX. Then for fetching the BCD number in the data segment, we use move BX comma BCD number. Then we are going to clear the CX register by using move CX comma 0. Next, we will compare this BCD number with the 0. If the BX register contents are equivalent to 0, then the jet flag will be set to 1. If BX content is equivalent to 0, else, that is BX contents is non-zero, then the jet flag is equivalent to 0. If the BX content is 0, then the jet flag will be set to 1. So this condition is true. The control will be transferred to loop 1 where we can terminate the program. Else, the subsequent instructions will be executed. So if the BX register, which is nothing but the BCD number, is not equivalent to 0, now we will see the conversion. Now first we will fetch the lower 8 bits of BX register which are in BL register, that will be loaded into AL register. So now AL will have the lower 4 bits of the BCD number. Now we will subtract AL with 1. Then we go for decimal adjust after subtraction. This instruction is used for converting the result obtained after subtraction into the packed BCD number. Next, after converting into packed BCD, we will place back this one into AL register. Then the upper 4 bits, that is BH registers, we will fetch into AL register by using the instruction move AL comma BH register. Now we will subtract AL with the carry flag. So for that we use SBB instruction, which is subtract with borrow. So when we are done previously a subtraction, if any carry is generated, to handle it, we are going to subtract along with the carry flag. So now the upper 4 bits of BX register, that is BH register, is loaded into AL. So when we are subtracted here, if any borrow is taken, so that we want to subtract here. So for that we use this SBB instruction. If there is no carry borrow is generated previously, now this BH contents will not be altered, which are there in AL register. Next, once this process is done, the AL register contents, either it may be subtracted with 1 or it is remain same. So now AL register contents will be converted into the packed BCD. So for that we use the instruction decimal adjust after subtraction. This instruction will do the AL contents will be converted into unpacked BCD number. Next, we will fed back this AL register converted into packed BCD into the BH register by using move BH comma A. Then we go for incrementing CX register. If after incrementing the CX register, unconditionally we will go back to loop 2, where this loop 2 is having compare the BX with 0. So like this, every time the given BCD number will be subtracted with 1. For every subtraction, the CX contents will be incremented by 1. So this process will be repeated until the BX register content is equivalent to 0. So how many times we are going to subtract? The same number of times we are going to increment the CX register. So once this BX is equivalent to 0, that indicates the BCD number is converted into binary number, which is there in the CX register. So when it is equal, we will go for terminating the program, so which is there at loop 2. So what we have at loop 2? So loop 1. In the loop 1, first we will fetch the address of the binary number which is reserved in the data segment into the DI register. Now our result is there in the CX register. Now CX register contents will be loaded into the memory location whose address is specified in the DI register. So once the BCD number is converted into the binary number, we will terminate the program by calling int21h. As we want to return to the DOS prompt, we will call the function which is at 4ch with the equivalent code 4ch. So for that, first we will load the 4ch into AX register and we will generate interrupt21h by using the instruction move AH comma 4ch followed by int21h. Now we will see the entire program at a glance. First we will write assume cs colon code comma ds colon data So this assume directive is for requesting the assembler for reserving the memory for code segment and data segment. Next, we will declare the data segment by using the segment directive, which is a start of the segment. Ends is end of the segment. As these two are corresponding to data, we will proceed that for me data segment followed by data index. So whatever the entities are there between data segment to data index, those are corresponding to data segment. So in this data segment, we are declaring one input variable, that is BCD number equivalent to 4576H. Next, after converting this BCD number into the equivalent binary number, so for that we will reserve a memory by using the variable name bin num dw, that is 16 bits, and it is uninitialized. So whenever you have dw question mark or dw dup question mark, it is for reserving the memory. Now we will see the code segment. The code segment will be started with the directive the segment as it is corresponding to code. So you'll write code segment. Start is the label which we are giving the start of the program. First we have to load the data segment address assigned by the assembler into the data segment register in that manner. So first we will load the address of the data segment, which is data, into AX register, from AX register to data segment register. Then we will fetch the BCD number, which is a input for the program, which we are declared under data segment. So the BCD number will be loaded into BX register. So for every BCD number, we are going to subtract with -1 repeatedly. So for every subtraction, we are going to increment the CX register. So this will be repeated until the BX register content is equivalent to 0. So for this purpose, loading the binary number equivalent, we will clear the CX register by using move CX, 0. Otherwise, we can write XR CX, CX. Both are valid. Next, we will compare whether the given BCD number is equivalent to 0 or not. So for that, compare BX, 0. So what are the program which you are writing? It will be repeatedly subtract with -1 until the BX register content is equivalent to 0. So when BX content is equivalent to 0, the jet flag will be set to 1 if BX is equivalent to 0. So as this condition is true, it will be go to loop 1. So what we are going to write in loop 1? At the loop 1, we will load the result into the memory and will terminate the program. Suppose if BX contents is not equivalent to 0, in that case, the jet flag is equivalent to non-zero. Then this condition is failed, so subsequent instructions will be executed. So in the subsequent instruction, so out of this BCD number, which is a 16-bit, first we are going to be load the lower 8 bits into AL register. Then we will subtract with -1. Whatever the result is obtained, this will be converted again into unpacked BCD number. So move AL, BL. So now the lower byte of your BCD number is loaded into AL register. Now we will subtract AL contents with 1. After subtraction, the result which is there in the AL register, that will be adjusted into unpacked BCD by using the instruction DAS, which is decimal adjust after subtraction. So after every subtraction, we will check whether you are taken any borrow. So for that, we are going to subtract SUB AL, 00. So this will be subtracted the carry flag. Suppose if carry flag is not taken, then conversion will not be there. So now this converted unpacked BCD number which is there in the AL, that will be moved back into BL register. Then BH register, that is upper 8 bits of the BCD number, is loaded into AL. Previously, if any carry is generated, any borrow is taken, that will be subtracted here. Then it will be converted. Suppose if no borrow is taken, so this AL contents will not be altered, which is nothing but BH contents will not be altered. So if any borrow is taken, that will be subtracted and it will be converted into unpacked BCD, and the AL register, which is a unpacked BCD after conversion, will be loaded back into BH register. So for every one step of subtraction, we are going to be increment the CX register. So once one subtraction is done, then we'll go back to loop 2 without conditional checking, which is unconditional jump. So here we are going to jump to loop 2, where in the loop 2, we'll compare the BX register with 0. So this process will be continued until BX is equal to 0. Once BX content is 0, we will fetch the address of the binary number, which is in the data segment, into DI. So here you will write move DI comma offset of binary number. So which is for fetching the offset value of the binary number into DI register. So the result which is there in the CX register, that will be loaded into the memory location in the data segment, which is already fetched the address in DI register. So for that we use the instruction move in square braces DI comma CX. Now this instruction will load the data segment memory reserved for binary number with converted binary number, which is in CX register. So once this is done, then we can terminate the program and we can return to DOS prompt by using the int21h with the function call with the 4ch. So for that, first we will load move ah comma 4ch. Then we will generate int21h. Then we will end the code segment by using code ends. We will end the program by using end directive. The start label for the program is start. So this is the program for converting the BCD number into binary number. So in this session, we have discussed 3 programs. One is for displaying a message on CRT. The second program we have discussed for converting a binary number into gray code equivalent. The third one, we have wrote a program for a BCD number converting into equivalent binary number. So thank you. So total 3 programs we have discussed in this session. So few more programs we will see in the subsequent classes. Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.